Welcome. I have the pleasure of welcoming you back to the channel, to this lesson. We meet now for a lesson in physics, Form 3. This is Form 3 physics. All right. In particular, we are meeting for a topic called measurements. It's measurement 2. Measurement 1 is, you met measurement 1 in Form 1, I think. In Form 3, we are meeting again to look at more measurement skills in physics. And we meet now for a topic called measurement 2. All right, so without wasting your time, let us define a very important concept that relates to this topic, this lesson, and that's called physical quantities. Physical quantities. All right, so for the sake of this lesson, we shall define a physical quantity as just anything, anything that can be measured. Anything that can be measured is called physical quantity. So anything that you can measure in the lab, for example, you can measure the length of a wire, you can measure time taken for an event to take place, you can measure mass of a coin or mass of a bag of sand. Think of anything that you can measure in the lab in a practical. So anything that can be measured is called physical quantity. A physical quantity is anything that you can measure in the lab. And remember that a physical quantity has two parts. A physical quantity has two parts. Let's suppose we have measured time. Let's say you measure time taken for an athlete to run from one point to another. Time, let's say you got time of 10 seconds. Let's suppose it took someone to run from one end of a football ground to another. It took 10 seconds to do that. So we are saying if every physical quantity has two parts. It has the size, which is called the magnitude, numerical magnitude. Okay, a physical quantity has a numerical magnitude, but it also has another part, which is the unit. So we are saying every physical quantity has two parts. It has the magnitude, which is the size, how big it is, and the unit. A quantity that does not have a unit attached to it is meaningless. It's meaningless. So a physical quantity must be fully presented with its size or magnitude and the unit. The unit doesn't have to be an SI unit, it can be any unit. So for its completeness, a quantity is supposed to have the magnitude, how big, and the unit. For example, let's suppose that you have a mass of, your body has a mass of 90 kgs. This must be huge enough, very huge. So the 90 part is the magnitude. 90 is the magnitude, while the kg is the unit. All right. So we just defined a physical quantity. We are saying that a physical quantity is anything that can be measured in the lab, all right, and that a physical quantity has two parts, namely it has the magnitude, which is the size, indicating how big it is, and a unit. Alright, so we have two types of physical quantities in physics. So we shall discuss the two types of physical quantities. We have what is called fundamental quantities. Fundamental quantities, also known as basic quantities. So we have fundamental quantities, also called basic quantities. Fundamental quantities or basic quantities. The other type of quantities is known as derived quantities. So quantities can be classified into fundamental and derived. Alright, so let's define each of the types of physical quantities, starting off with fundamental quantities. What are fundamental quantities? Or some say fundamental quantities. Fundamental or fundamental is alright. So fundamental quantities are defined as quantities which are not defined in terms of other quantities. In other words, fundamental quantities are the most basic quantities. In other words, they are starting units. They are starting quantities. Everything measured starts with fundamental quantities. Okay, you look at a fundamental quantity as a brick. Okay, in a brick, a building starts with a brick, a small brick. All right, and many bricks together will form a building. All right, let's suppose these are bricks. These blocks represent bricks. All right, so we have as many bricks as possible joined together using mud, all right, or mortar. So you have bricks joined up together to form a wall, for example, in a building. All right, so each of the bricks is a fundamental part of the building. Fundamental. It's a fundamental part, all right, because a building starts with a brick. So it takes many bricks joined together using mortar, pestle, and mortar to make or to come up with a wall of a building. All right, so basic quantities, therefore fundamental quantities, are the building blocks of all physical quantities. They're the building blocks. That's the starting quantities. We call them basic quantities. So we are saying that fundamental quantities or basic quantities are quantities which are not defined in terms of others. In other words, these are independent of other quantities. They are independent of other quantities. All right? So in physics, there are 7 in number. There are 7 fundamental quantities in physics. And then your syllabus requires that you should know all of them. You should know all of these. You should know all of them. You should know their units, SI units. You should know their SI units. You should also know their symbols. You should know their units, and you should also know the symbols of their SI units. All right, there are not many. All right, so you don't need to worry about memorizing them or knowing them by heart, because after all, there are not many of them. There are just 7 of them. All right, so what are these? Okay, so we have length. Length is a basic quantity because you can measure it directly using a ruler, a tape measure, or any other appropriate instrument. Length. Remember, Length is just distance. Length is the same as distance. All right? Length is the same as distance. So distance is measured using a ruler, a measuring tape, or a vernier caliper, a micrometer, screw gauge, any other instrument which is suitable depending on the size of the length. The SI unit of length is the meter. The meter, okay? And the symbol for a meter is small m, not capital M. Small m is used to stand for the unit of a meter, which is the SI unit of length. Other units of length include the kilometer. Other units, you have the kilometer, okay, where a kilometer is the same as 1,000 meters. You have a millimeter. A millimeter is just the same as 0.01 meters, centimeters, and so on. Centimeter is 0.01 meters, and many others. All right, these are the common ones. All right, the common ones. But take home that the SI unit of length or distance is the meter, full stop. These are just other units. And you'll be required to convert from one unit to another. You may be given other units for them to bring them back to the meter. All right, that skill can be done later, can be developed later on. But for now, it is sufficient to say that the SI unit of length is the meter. All right, another quantity, basic quantity or fundamental quantity is mass, which we define as mass is simply the quantity of matter. The quantity of matter. Mass of a substance is the quantity of matter. All right? So by quantity we mean how much. How much of something is called mass. All right? It is also referred to as resistance. Mass is also defined as the resistance to change. Resistance to change in motion. The resistance of a body to change is motion. All right, but for now, at this level, we shall limit our definition of mass to the quantity of matter. That's all, the quantity of matter, how much matter there is in a substance, in an object, is called mass. Okay, but later if you take physics further, you shall define mass as the resistance of a body to change its motion. All right, it is also called inertia. Mass is also called inertia. That is, if you take physics further or beyond this level, you'll be told that mass of a body is simply its inertia. Its inertia or simply resistance to change. All right, mass is measured in kilograms. 1 kg of anything is the same as 1,000 grams. So 1,000 grams of any material is the same as 1 kg of that material. Other units include milligrams. 1 milligram, for example, is the same as 0.001 grams. All right, 1 milligram is the same as 0.001 grams. Okay, 1 centigram is the same as 0.01 gram, and so on. Okay, So these are just other units of mass, but it is sufficient to attach a kg to the mass of a body as its SI unit. Remember, SI is short for Système International des Unités. S stands for system or system international or international des unités. All right, so in English it's called International System of Units, but where these are made, it is called, in France, it is called Système International, SI, because you would be wondering why it is SI and not IS for international system. All right, so these are units, the units of physical quantities or basic quantities which are used internationally. Wherever physics is taught, these are the units of the physical quantities, the basic quantities. Another one is time. Time is measured in seconds. The symbol for second is just a small s. Please take note, it's not supposed to be capital S, but small s. All right, kg, similarly, kg is all right. Meter is small m. And then we have thermodynamic temperature of a body, which is based on the SI unit called Kelvin. The Kelvin is K, take note. But when you are writing this in words, it has to be small k. Small k, Kelvin, not Kelvin with capital. If you put capital, some strict examiners will mark this wrong, because Kelvin with capital K is the name of a person rather than a unit. All right, but these are just minor issues. It may not be marked wrong if you capitalize the K, but strictly if you are writing a book, a physics book, and you would like to state the unit of temperature, thermodynamic temperature, the K in the word Kelvin should be small letter, unless you are writing the K in capital letters. That's all right. Or electric current, which is the flow of electric charges, electrons in a circuit, is has the SI unit called ampere, or ampere, some prefer to say ampere. Ampere is a French, A-M-P-E, with an accent there, all right. Ampere is French. In short, it's capital A. Take note also that you don't write this as capital A, then M-P-E-R-E. When you're writing this in full, you don't have to capitalize the A there. You are writing this in full, it has to be small a, then M-P-E-R-E. Okay, so these are just minor issues relating to units. All right, SI units, which are named after people. So ampere is like that. And then we have luminous intensity, which is the amount of light being produced by a body. So this is measured in units called candela. It is the same word from which we get the word candle. Candle means light. Okay, so candela means light. In short, is CD. And then you have amount of substance. Please don't confuse amount of substance with mass. These are not the same. They are different. All right, and the amount of substance is used mostly in chemistry. So if you take chemistry, the word mole, the term mole is the unit of amount of a substance, mole. All right, in short, it's just M-O-L. So once again, make sure you know all these off by heart, because your examiners would require you to state the units and their SI units, as well as the symbols. Please, where I mentioned that the symbols should be small letter. You have to strictly adhere to that requirement. So the meter is just small m. Then you have kg, small k, small g. Second is S. Kelvin is capital letter like that. Ampere is A like that. Candela is CD. Small c, capital, small c, small d. The more like that. So you must know all of them. There are just 7 of them. So anything that we have not mentioned on this list, it means it's not basic quantity. We proceed to look at another class of physical quantities, which is called derived quantities. From the word derive, to derive, what does it mean to derive something? To derive simply means to obtain. Okay, now in other words, derived quantities are quantities which are obtained from combining 2 or more basic quantities or fundamental quantities. To derive simply means to obtain. All right, so we shall define, therefore, derived quantities as the quantities which are expressed in terms of the fundamental quantities. All right, so you can combine 1 or 2 fundamental quantities to obtain derived quantities. To derive means to obtain something. Yeah, so for example, I'll give you an example. Speed. Let's suppose you are looking at the speed of an athlete, speed of one running. Okay, speed is simply distance. It's found by dividing distance by time. Okay, so look at this. Distance is basic or fundamental quantity. Time is also basic. So these two are combined by dividing to obtain speed. Therefore, speed is a derived quantity, because it's obtained by combining 2 basic quantities or fundamental quantities: distance, which is length, and time. The world is full of these derived quantities. There are many of them. In fact, we can fill them up into this book. If we are to list them down in a book, we end up filling the entire book with them. Okay, unlike basic quantities or fundamental quantities, there are only 7 of them. But we can combine these derived quantities either by dividing or by multiplying to obtain thousands and thousands of derived quantities. All right, so it's just some of them. I'll leave you with an assignment to look for more in books. All right. All right, so some of them here include moment of a force. Moment of a force. What is moment? At this moment. Okay. Moment of a force is not about time. It is about turning. Let's suppose that you have a ruler supported at some point here. You're holding a ruler, you're supporting it at some point, which is called the pivot. And you apply a force F, force at some distance from the pivot D. All right. So moment M is simply the force multiplied by the distance from where the body is turning. All right. In other words, moment of a force is simply the product of the force and the perpendicular distance from the turning point. Don't worry about this. This will still come out clear in your Form 3 physics topic. It's a topic on its own. It's called moment of forces. The unit of moment is Newton meter. In short, is written Nm. So, physical quantities can also be expressed in terms of base units. Base units are the units of the fundamental quantities. Let me show you this particular example. We just said moment is equal to force multiplied by perpendicular distance. All right. What is the unit of force? You know it is the Newton. What is the unit of distance? You know it is meter because that's length. And a Newton is also the same as a kilogram meter per second square. So this multiplied by a meter shall give you a kilogram meter squared per second square. So this is called the base units of moment. Base units of moment. It's a practice that you have to do in order to convert the unit of the derived quantity into its base units. Another one is work. Work is found by multiplying force times distance. All right. Let's suppose you are pushing a body, all right, over some distance d. All right. So the distance, the force applied multiplied by the distance over which you push this is going to give you work done. Once again, the unit of force is the Newton, and the unit of distance is the meter. Therefore, the unit of work done is also called a joule, where 1 Newton meter is the same as 1 joule. All right? But you can also express this in terms of the base units. 1 joule of work done, 1 joule of work done is the same as 1 Newton meter. But what is a Newton? Once again, a Newton is the same as 1 kilogram meter per second square multiplied by a meter. A meter by a meter shall give us the kilogram meter square, then per second square. Okay, so don't worry. These are just what we call, they are the same units but in form of derived units or base units. All right. So a question can say, calculate the work done when a certain force is applied on an object over a certain given distance. Calculate work done. Remember that work done is in joules, but you can also present it in terms of base units. So you have to, it's a must for you to know these base units of different quantities. All right. You must know these. You'll be required to present your answer in terms of base SI units. Energy is also a derived quantity. And remember, energy is ability to do work. Is also ability to do work or simply work done, which means that energy is also in joules. And we just mentioned that a joule is the same as a kilogram meter square per second square. All right, so these are things that you must know. Derived quantities. Another one is pressure or power. Remember, power is work done divided by time, also defined as force multiplied by speed, or FV. All right, so power, since we are talking about joules, power work done is joules, time is in seconds. Therefore, in the base units is going to be joule. The SI unit of power is joule per second, which is called a watt. Watt, like this. All right, the watt. In other words, the watt can also be presented in terms of base unit, base unit. So 1 watt is the same as 1 joule per second, yes, per second, which is the same as 1 kilogram meter per squared per second cubed, So make sure you know all these and many others. I would actually leave you with work to look up the other examples, because there are many of them. There are thousands of derived quantities. All right, there are thousands and thousands of derived quantities. Another one is pressure. Remember, pressure is force divided by area. This is Newton. Pressure is in newtons. This is in Newton. In Newton, area is a square meter. That means pressure is going to be Newton per square meter, which is the same as in Pascal. All right. Again, you can write a Pascal in terms of base SI units. All right. Another one is charge. Q. Charge is simply current multiplied by time. Okay. So the unit is going to be, current is in ampere, time is in seconds. That means charge, coulomb, one coulomb of charge is simply 1 ampere second. All right, don't worry about all this. Just know the examples of the derived quantities, these ones, and how they are defined. Look up the books, different books, physics books, for other examples of physical quantities. Once again, my name is Mr. Pochilola. If you are joining us for the first time on this platform, don't hesitate to subscribe. Consider subscribing to the channel so that every time I post a new video lesson, you are the first one to be notified. Now, having looked at physical quantities, which we said they are of two types, namely basic quantities and derived quantities, now let's look at standard notation. Standard notation, also called scientific notation. It's just a way. Standard notation is just a way of writing numbers that are too big, either too big or too small. Sometimes in physics, you may end up measuring a quantity and you get a very huge number. Let's say you got a number such as 10,000 grams, right? This is too big a number. So as a scientist, you must devise a way of writing this in a manner that is more accurate, that maintains accuracy, and it will not actually lead to omission of some important digits like zeros. All right, so we use standard notation or scientific notation for presenting numbers or values that are either too big or too small. All right, for example, let's consider a number such as 0.000 and 1. This is very small number, if you can see. All right, so you need to write this number in standard form. Okay, what is the danger? If you write a number like this, chances are that you can leave out a 0, and that will change the meaning of the number totally. All right, so how do we write this properly? To write this properly is to write it so that the number lies between 1 and 9. 1 and 9. Okay, so to write this in standard form simply means to write it so that it lies between 1 and 9. or 1 and 10. Okay, 1 and 10. Or let's say 1 and 9, say 9, and so on. Okay, so to write a number in standard form or scientific form simply means to write that number in a way that it lies between 1 and 9. All right, so let's go back to that example I gave. So we have 0.00000000001. Okay, so in order to do that, all you have to do is to shift the decimal. Notice here the decimal is somewhere there. All right, so you shift this decimal until you reach a point where you have a number that ranges from 1 to 9. So you do this, you simply count how many zeros: 1, 2, 3, 4, 5, 6, 7, 8, 9. I've shifted my number such that it has gone up to 10. I've shifted it in the decimal point 10 times. So in the end, you're going to have 1. So the decimal now looks to be there, appears to be there. So I will have 1 multiplied by 10. How many times did I shift and which direction was I moving? I was moving from left to right, this way. Okay. So the number now becomes 1 times 10 to the power minus 10. Take note of that. This 10 here is just the power to which the decimal has been raised to the number of times the decimal has been shifted. So in this case, I've shifted the decimal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Ideally, I go up to there because I'm looking for a number that lies between 1 and 9.999. All right, so the number therefore, the same number, this one, is going to be 1 times 10 to the power minus 10. This number has a better form of presenting it, and it's easier to tell. It also shows us the number of significant figures. It's up to 1 significant figure, this one. It's even neater to present than writing it in terms of the decimal point there. All right, so let's see what it means by presenting a number in its standard form. All right, let's look at this other example. Yeah, this is the same as, suppose the number is 0.000 0000001. Okay, so again, you shift the decimal point until you get a number which lies between 1 and 9. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9. Then you have 1.0 times 10 to the power minus 9. Okay, this is so easy to do. You can practice this with any other decimal number until you are sure, you're convinced. All right, let's look at another number. For example, this one. Let's say we are looking at 1 billion. So you do the same. So we have 1 0 0 0 0 0 0 0 0 0. Okay. So how many zeros do we have? We have 12. We have 9 zeros. Now the decimal this time is at the end. It's like if you put a decimal, then you shall have 0 0 0. Okay, so in this case, you also have to shift the decimal until your number lies between 1 and 9.999. So you shift 1, 2, 3, 4, 5, 6, 7, 8, 9. The point now is there. So the number now is going to be 1.00 times 10 to the power. How many times did I shift the decimal? It's 9 times. So the number now is going to look like that. A bit more decent than it was before. The danger here is that if you write your number like this, you can drop the 0 and it will change the meaning of everything. All right, so this is a better form of presenting it than before. All right, I would like to leave you now. When we meet again, I'm sure to bring some questions which you are going to use to practice what we've discussed so far. Once again, my name is Mr. Pochilola, wishing you a beautiful night tonight. It's night already here in Switzerland, and I hope it's also night where you are. For the time being, bye-bye. Take care of yourself and work hard. We're waiting to meet you again in the next lesson. In case you need notes, books, I have plenty of those. I'll be glad to share with you. Just contact me on the numbers that are shared on this platform. If you need papers to practice, abundant of papers for you to practice. Bye-bye for now. Work hard.